Share screen, PowerPoint. I think that's it. Can you all see? I hope.
Yes, you might want to enter presentation mode.
There we go. Minimize that. Move that up there. Okay, I think I'm ready to go. Hello, I'm Glen Hunter. I'm a master's student at the University of St. Andrews, and today I'm going to be talking to you about the creation of massive stars and what theories are present for them and kind of how observations are dependent on them. And we'll kind of go over them and kind of link to kind of project work that I'm doing at the moment. So a little bit about me. I'm still relatively early in my academic career. I'm still an undergrad, but I have dabbled in a little bit of kind of project work already, going from like atmospheric chemistry, gravitational dynamics and galaxies, synthetic observations I'm doing for my master's project, and I'm also kind of a keen part of the Astronomy Society here in St. Andrews, where this is the picture in the top right kind of shows I'm happiest behind a telescope. I'm about to start my PhD at the University of Heidelberg, dependent on the current pandemic situation, but hopefully as time progresses, that'll change. So as I mentioned, I really like being behind a telescope, and I really like to take pictures of very pretty things that we can find in the night sky, such as this beauty. This is an image of the Orion Nebula that I took a year, 2 years ago almost, where we're using the 16-inch telescope we have in St. Andrews. And the interesting thing about this, along with it being a very, very beautiful image, is that there's a lot of star formation happening within this region itself. I don't know how well you can see, if you can see my cursor, but if I circle around here, there are kind of 4 massive stars referred to as the trapezium, which are radiating so much energy that they've kind of blown out the cavity in the region that they formed in, creating this kind of beautiful effect. However, this is not the entire star forming region. If we extend out, the Orion star forming region extends the entirety of the constellation of Orion. So the big orange star up here is Betelgeuse, which is this massive star that people were hyping about potentially going supernova a couple of months back, but luckily it's not gone yet. And the Orion Nebula is down, I don't know what, around this area. But you can see these kind of cloud dusty structure occurring across the whole length of the Orion constellation, and this kind of spans an order of many parsecs. So to give an overview about what I'm going to be talking about, I'm going to be going kind of over an overview of the low mass regime in terms of star formation, because it's kind of good to kind of have that cemented knowledge. We then discuss about the differences between the low mass and the high mass regime, because physics gets a bit kind of troublesome for forming high mass stars. The current theories that we have for these, so how to form high mass stars, and then some observational evidence behind them. And then I'll talk about my project that I'm working on at the moment that kind of bridges that gap between theory and observations. So to begin, in the low mass regime, you have this kind of giant cloud, as I showed in the Orion region. And within that, you'll find kind of denser structures referred to as cores. Now, these cores can form due to kind of gravitational shocks, where, for example, a nearby supernova has gone off that kind of shocks the material and then kind of creates these dense regions. And once these regions become dense enough, they undergo collapse or gravitational collapse. And as a result, this thing kind of shrinks down in size, getting hotter and hotter. And because it's getting smaller, it's spinning up. And as a result, you get this hot static object forming in the middle of the region, which is and that kind of was what we refer to as a protostar. And as the protostar evolves and the system evolves, the disk forms due to the conservation of angular momentum. And bipolar outflows come out of the star to kind of take away the excess radiation coming out, or excess energy. And over time, the system kind of settles. You eventually just get left with the disk and the forming star. And as the star kind of contracts more, initiates hydrogen fusion, we get our planets forming, and it kind of makes you and I, or home for you and I in a sense. However, things are not as smooth going to the high mass regime. You initially thought it would kind of go up to, you just upscale what we know from the low mass, but the problem with having a kind of big, massive core that forms a massive star is that there's many genes masses within them. So kind of many different regions which can collapse into a star. The medium itself can be very turbulent, disrupting these kind of static cores and shifting them all around. High mass stars don't require, or are not as affected by magnetic fields as much. So this kind of becomes apparent. And then when you're forming such a massive star, since it's so hot, the radiation pressure coming off of that star halts the inflow of matter going in, and as a result just kind of pushes away, and you don't get, or in theory you wouldn't get as massive of a star as a result. But there are many theories that kind of come across that kind of radiation barrier in a sense. So today I'm going to discuss three theories in this kind of little section. So we have protostellar collisions, monolithic collapse or core accretion, and then there's going to be the competitive accretion model as well. So jumping right in, we're going to the protostellar collisions. So as the name suggests, you get two protostars or more, you smash them up at each other and hope that they result to a massive star as a result. Which works in theory. So you can have two stars coming together, orbiting each other, one pulls matter from the other, and then that matter kind of accretes onto the star. However, space is big. Space is very big. And in these kind of environments, you don't really have protostars being close enough to kind of interact with each other to the point that they collide. And this is only kind of really viable in very big clusters of stars where there's lots of kind of massive stars towards the center of them. And they're also quite violent events. So this image is of a star forming region with the visible light in the background. But this kind of hatched area in the middle is what a radio telescope known as ALMA, or the Atacama Large Millimeter Submillimeter Array is what it stands for, has detected this kind of these regions, or this kind of area where it's kind of highly energetic. You see a lot of matter being sprayed out, and upon further analysis, they see there was the interaction of two protostars, and they are still interacting with each other. And as a result, you kind of see this explosion almost. And when you look back in the data, they still see that these protostars are still there, they still exist, and they haven't coalesced into one singular object at the moment. So it's kind of put a hole in that kind of theory, because it results in a lot of matter being dissipated and the protostars still exist there. So we go into another theory called core accretion, or the turbulent core model. And this is the one that kind of is close to the idea that's presented at the low mass regime. You take so in low mass, you have small core, make small star. So if you upscale it, you've got big core making big star. And what happens is that the turbulence that is present within this core stops the the core from fragmenting into smaller cores. Now the idea is quite nice because it would mean that the initial mass function, which is basically an idea that there's is a way of kind of counting how many stars you have of a certain mass, would correlate well with the core mass function, basically similar case, but protostellar cores. And a good kind of observational case is that you still get these kind of outflows and angular momentum conservation that can cause the accretion disks to kind of feed the matter into the star. Now, I do have a lovely movie given by Rosen et al. In 2016. So what we have here is a massive cloud collapsing on itself, or a massive core collapsing on itself. And you see the matter feeding into the central star and all the kind of various fluid dynamic effects that are happening. And eventually there'll be outflows coming out from the poles of the star that kind of create this cavity and then feeds towards the accretion disk. At some point, the accretion disk fragments, and you might see just down here, there's a couple of stars. And this is allowed in the theory because it's as a result from the accretion disk fragmenting rather than the core itself. However, if we turn to observations again, oh, let's play again. Before, there we go. We don't really see these massive protostellar cores. And if we do find them, we follow up with instruments or upgraded instruments. We find that they don't really they kind of are not one big core, but instead are multiple cores. They are more multiple cores. And it's also not known how these cores can become so massive in the first place from current understanding, because these environments prefer kind of smaller cores to form. And even with turbulence preventing from fragmentation occurring, some tests suggested that fragmentation still occurs. However, there's been kind of debate back and forth that the radiation coming off of the massive star kind of stabilizes everything and still allows for that massive star to form. Now, the kind of competing theory to the turbulent core model is the competitive accretion theory, and is one of my favorites. So you take a massive cloud, or kind of a cloud, and you allow the cloud to collapse, and you still forming an environment where multiple low mass stars would form normally. However, if you think like a valley or a sink or something like that, at the very bottom of the sink, there'll be a lot of flow of matter towards it, or towards the central star, whilst all the stars outside, more up the potential well, don't have as much of an inflow of gas towards them. And instead they're having to fight for whatever gas passes by them, in a sense. And this is where the idea of kind of competitive accretion comes from, because they having to compete to get the matter. But however, this model suggests that massive stars can only form in clusters. And then when we do turn to our observations, we do find a lot of massive stars do occur in clusters. A simulation run by Smith et al. 2019 kind of illustrates this point, that you take the kind of larger cloud and you allow it to collapse, and you get multiple stars forming as a result, with the most massive star being at the center of this potential. However, like most models suggest, there is a kind of drawback to these ideas. Since it requires a much larger reservoir gas to occur for, in terms of theoretical models, it's hard to track the magnetic fields and the outflows properties and radiation fields as well from these forming stars. And so there's this kind of debate that's saying that since they're not accounting for the radiation feedback and such, then the stars are over accreting per se. So there's kind of researchers currently are trying to update their codes to account for this radiation feedback. Turbulence, again, which is is a main factor in a lot of these ideas, can still disrupt the inflow of material as well, and may drive it towards another star instead, or distribute the material a bit more evenly. It's also noted that the accretion rates that are found in these regions are not sufficient enough to form a massive star within short timescales. So short massive stars live, or go by the phrase of live fast, die young kind of thing. So they're not around for very long. So in order for them to reach the mass they have to accrete matter for much longer than what their lifetimes are. And it also doesn't really explain how we find isolated massive stars. So we do find there's massive stars that exist on their own away from any cluster. So, and we're still trying to figure out how those massive stars form. When we look to observations though, things get quite interesting. So here we have an image from the Glen survey and looking at what's called an EGO, which stands for extra green object, I think. And this is a mid-infrared image. I think it's near mid-infrared image. And this region has been analyzed by various authors over the years and has been noted that initially it was like only one core, or maybe 2 or 3 that kind of points towards the tiny turbulent core model. But the latest kind of observation of this region, taken back in one of the kind of more updated ALMA cycles, has found that there's about 19 cores, or star-forming cores present within this region, which kind of points towards the competitive accretion idea that has been presented prior. However, as noted by Siganowski et al. In 2017, further kind of theory development needs to be carried out in order to kind of investigate these regions further. So, how do we link these kind of theoretical ideas, such as like the turbulent core model, competitive accretion, to what we see? And the answer is we create synthetic images. And this is something that I have been doing for past couple of months as part of my master's project. And I'm going to kind of give an overview of what synthetic images are and what results we found by doing this. So what is a synthetic observation? To quote Haworth et al. In their kind of 2017 review paper on synthetic observations, synthetic observations are prediction based on theoretical models of the manner in which a particular astrophysical source will appear to an observer. So you take this kind of simulation or model, you run it through various codes and whatnot, and you ask yourself, what happens if I point a telescope or observe it with a radio telescope or something like that, and then try and recreate that image in the essence of that thing you're observing with. A good example of this is from Medina et al. In 2014. Very, very beautiful image that is pretty really impressive. And this is of a H2 region that they've simulated and have applied the different kind of techniques that are required to generate synthetic observations. However, in the project that I'm working on, we don't do optical light. We look in the radio. So how do we create these synthetic observations? So if you look at this kind of diagram to the right, there's different layers to it, and at different points in that different kind of collections of those layers result in kind of different synthetic observations. So you originally have your dynamic model, which most cases is a hydrodynamical code or in-body simulation of the region you're interested in. Your emissivity is basically what optical properties you want to introduce, which is a result from chemistry. And if you collect this together, and you can get kind of a base idea of what your region should look like. Now, if you add microphysics to that, that accounts for like things like your thermodynamics, your heating, your cooling. And then if you add radiant transfer to that, which is basically simulates the light propagation from these regions, then you have a bit more of a kind of more detailed picture of what's coming out and gives a kind of better idea of what you're actually looking at. However, it's still this kind of pristine object that doesn't account for kind of instrumental effects. Now, if you add instrumentational effects to it, and effects such as like the Earth's atmosphere, kind of dust opacity along the way, then you get a kind of truer image of what this region would look like to an observer on Earth. And in the project that I'm working on, we have included most of these ideas, right down to the instrumentational effects along the way. So my MPHYS project is to generate a synthetic dust observation of a high mass star-forming region as observed from the Atacama Large Millimeter Submillimeter Array, which is a radio telescope in Chile. And we're to analyze these images as if I were an observer. And then we can compare our observational results to the theoretical ones that we've seen from we can get from the simulations themselves. So the numerical model is a collapsing callout run in the repo hydrocode. A repo is a wonderful hydrocode. I had the pleasure working with it a couple of summers ago. And is originally designed to do cosmological simulations, but a lot of people have kind of downscaled it to work with star-forming simulations. The good thing about it has a very good chemical network, as well as, and it can account for all the kind of thermodynamical processes that are present within the region. A thing to note about these kind of star-forming simulations is that when a kind of region gets to a certain density, a particle will pop into existence referred to as a sync particle. So you might see in this image, you see these kind of red and blue particles popping in, and this refers to kind of forming stars. So these sync particles can continue gaining mass over time. However, they don't really halt the mass inflow until you stop the simulation. So they're kind of a good proxy for star formation, but maybe not so much for like further star evolution. Now, we take the last frame of that simulation and we run it through a Monte Carlo radiate transfer code called Polaris, which basically takes the sync particles above a certain mass regime. In this case, it's a 1 solar mass, which means stars that are basically the sun or bigger, and allows them to kind of heat the environment around them, around the region, and then simulates the thermal dust emission as a result from that heating. And it results in this image that you can see here. And one thing to note, since it's only dust emission, we can't account for kind of radio velocity techniques as a result, or kind of gauge dust temperatures throughout. So once we have the sky model, we have this kind of pristine object that accounts for the first 4 points that are illustrated in that kind of diagram I showed prior. The only thing left to do now is to introduce the instrumentational effects. So what we do is we take the sky model that is presented, and then we throw it into a simulation software or a radio astronomy software called CASA, which one of their tools allows you to create synthetic observations from radio telescopes, in this case for ALMA. And it creates this kind of dirty image that's very noisy. And then what we did is that we cleaned this image like you would as an observer, and primary beam corrected it. So basically it is observed due to many antennas and then kind of correct for those effects. And then what you're left with is this kind of image that my friends like to refer to as the eyeball image, because it looks a bit kind of like an eyeball. But it gives this it goes from this kind of really kind of clean, pristine image to this kind of everything's kind of not as clear or well defined. But this is what we would actually see with the telescope, or with ALMA, had this region been pointing at this certain part of the sky with these kind of atmospheric conditions. And I was quite proud of this result when it came out. So further analysis was carried out, or aside from the cleaning, to identify cores within this region. So we use a software called Astrodendro, which is a dendrogram software that you input it, the kind of minimum requirement, the minimum intensity region needs to be counted as a kind of source, the amount of spacing between them, and then what kind of resolution that you're working with. And it results in the kind of lovely dendrogram that I wish I exported, but unfortunately didn't have the time to get it out. And you can see highlighted in blue are the cores that are found with this method. And the interesting thing to note is that we're having cores range from about half a sun to over 100 suns in mass. However, there's one thing to note is that we're assuming a constant dust temperature throughout the entire region, which works kind of well for the low mass stars, but when you get to the higher mass stars or higher mass cores, they would generally be a lot hotter than the smaller ones. So we had that's something that we would account for. We had a complete chemical network, but unfortunately we don't. We can only assume the kind of dust temperatures. We only have the dust observations, unfortunately. But we can still do some interesting science with. So the question is, where are the sync particles that I've discussed before within this image? Well, here they are. So you might see in these kind of black, blue and green and yellow dots throughout. And you'll see that some of them, or a good majority of them, exist within cores, but a good portion of them kind of exist without. So we kind of been bashing heads together trying to figure out why the ones outside the cores are not emitting and what's the ones inside cores are emitting, and it's quite interesting the science that we kind of come up with. So in regards to the sinks existing outside of observable cores, it suggested that there's a potential sink mass limit that is needed to allow for them to contribute to the heating of the environment. But it also could be because there's limitations in the dendrogram method that could be used. In such case of this kind of region towards the kind of little bit to the right of the center, where you have this obvious kind of green dot. Oh, let me go back. I hit the wrong button. Obvious kind of green dot in the middle, and with a kind of really bright part associated with it. However, the dendrogram is just not finding it for whatever reason. So this could be due to we're not setting the right separation, we're not given the right kind of resolution associated with it. And it's kind of something that I need to kind of play with to kind of see what is required so that can be identified as a core itself. In terms of cores that have no sinks within them, so if you go to about a little bit left, so like this one here, it's quite interesting to see is like there's no obvious source of where this heating is coming from, but it could be suggested that the core kind of below it, there's a massive sink in there of about 50 solar masses, which would result in a lot of kind of a lot of heating in the environment. Might have been leaking some of that heating into that core above, and therefore Astrodendro is picking up that as well. But it could also mean that the detection threshold might not be correct either. So it's quite interesting kind of seeing where things are and where things are supposed to be, but not actually appearing. I have done this for multiple kind of maps, that's what I refer. So there are simulations where the kind of minimum requirement to be considered into the heating code is kind of lowered or raised. And there's kind of interesting results that I'm working with coming out. Some interesting correlations that are kind of come out with this. So if you take a core and sum the entire sink mass, the entire amount of sink, the total mass of the sinks within that core, and plot them against peak flux, integrated flux, and core mass, we see that there's a kind of an upwards trend, but it's not a strong one. I need to do the full kind of statistical analysis of that. That is kind of what I need to do for the next few weeks. And there is a kind of lot of plot points within the kind of lower mass regime that are not being seen because of the scaling of the plots at the moment. However, kind of more stronger correlation is the maximum sink mass within a given core. And there's a kind of stronger correlation towards the integrated flux and the core mass, making suggesting that the most massive sink particle within a given core is the one that's influential to the flux of the core itself. Due to it, so it's quite kind of an interesting kind of result we've observed as a result. So to conclude, there are many, many theories into the process of massive star formation. I've only covered 3 for today. However, from observations, it suggests that competitive accretion is a likely process. Observations suggest that a competitive accretion-like process is present in these massive star forming regions, and is probably the theory that kind of holds true. However, turbulent core models have been updated throughout over time, and are kind of requiring a more extended reservoir gas, and it might lead to a point where the theories kind of come closer together and kind of agree with each other at some point. As noted, synthetic observations can help link between theoretical ideas to observational properties, as noted in my project. And an interesting result from the project is that not all apparent cores contain forming stars, but there are correlations between correlations suggesting most massive stars in a core contributes to the core's emission. But yeah, that's all I have to say for kind of a whirlwind tour of low mass regime, high mass star formation, a little bit of what I'm doing. And I just want to thank a few people. I want to thank Dr. Claudia Sikanowski and Dr. Camilo Penaloza, who are my project supervisors at the moment, and Professor Ian Bennell, who's been a great mentor for me over the many years and has been the one that's kind of got me into star formation. I want to thank Dr. Rowan Smith at the University of Manchester, who has given me permission to present the data here, because she was the one who ran the original hydrodynamic code. And I also want to thank Dr. Paul Clark for getting me into kind of start the theoretical side of star formation, and to the STEM Village for hosting me today, and to you guys for listening. And I shall leave you with this lovely image of the Orion Nebula again, and I'm happy to take any questions that you have. Thank you.
Thanks, Glenn. I found that really fascinating. I'm an astrophysicist as well, so I'm not really a stellar astrophysicist. I'm more on the black hole side of stuff. So anything stellar I find really interesting. Thank you for that.
Anytime.
If anybody's got a question, feel free to pop your hand up or to stick it into the chat window. And in the meantime, I have a question, and actually it comes back to this image. It popped in my head right at the start. And that was, you often see these images of nebulae, and there's a whole bunch of science that gets done on especially star formation in nebulae. But how the depth of a nebula, we can see its height and width in this image, but how do we know how deep in it goes?
So the depth of them is kind of an interesting thing to work with or trying to figure out. Since a lot of these kind of images are only 2D, it's hard to kind of give an idea of depth to them. However, there has been work looking at kind of the line of sight velocity associated with these regions. The line of sight velocity. So if you take a spectrum of these regions and see how this spectrum is shifted, like red shifted or blue shifted, that can give an indication of the things moving towards you or away from you. And you can create these things called position velocity maps that can then be turned into position maps, and can give you an idea of what the 3D structure is like towards these regions. Personally, I don't know the full process of how this is done. from kind of straight from observations, but in terms of a theoretical perspective, it is kind of possible to do so. I hope that kind of answered your question.
It did. Thank you very much. We've got a question here from Natasha. Would you like to unmute yourself and ask it yourself, or would you rather I read it out?
Hello.
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 Currently training to be a secondary school science teacher.
Mm-hmm.
My specialty's biology, and my degrees have been in environmental science and wildlife conservation. So I'm fascinated by space and everything about it, but it's not something I've ever studied in much depth.
Mm-hmm.
Did anything you were taught in school inspire you to study star formation? I love teaching the space and universe topic to my Key Stage 3 classes at the minute, but I'd just like to know if there's anything I could do to ignite that love in kids.
Thank you for your question. I'm trying to think how I got into space, really. For me, how it wasn't so much what was taught at high school, but there was this book I had as a kid that kind of detailed different aspects of astronomy and gives all the lovely, pretty pictures behind it. And that just kind of got me really interested in like how do these pretty things form, and as I went through high school, the curriculum at the time didn't really cover space that much. I grew up in Scotland and was in part of the older curriculum. I know they're introducing astronomy and astrophysics into the physics curriculum now, which is a great thing, and I wish that I had, but it was more that my own kind of personal curiosity that kind of got me into it rather than what was in school. But to kind of inspire kids in school, I think lots of pretty pictures helps to kind of illustrate the point. So you can get like the photos of like star forming regions or of galaxies. That helps, but also kind of given a kind of tactile approach to things as well. I know that in certain outreach projects that the university does for science, one of the kind of astrophysics, kind of astronomy, space related ones is like build a comet that they make out of like dry ice and various other things. So it's kind of given to help kind of firm that understanding that even the things out in space can be recreated on the planet effectively. I hope that answers your question well.
Yes, brilliant. Thank you very much.
No problem.
If we don't have any more questions, I don't see any hands up, and there's nothing else I think in the chat. I will ask you as well, Glenn, if you could, I know this on your slide, but could you also pop it into the group chat, your Twitter handle?
Sure.
We can direct to you questions after this is finished.
Yes, give me 1 second. So my Twitter handle is @AstroHuntsman. Feel free to ask me all your questions there. And I try to keep give some pretty post pretty pictures of things that have imaged with the telescopes in St Andrews, because although I've got a very theoretical mindset, I do like the observations as well because I think they're just stunning.
Fantastic, and that just about wraps it up for today. Matthew will be back in the hot seat tomorrow, and he will be talking with, let me quick look, Kiri Thornley on protein coronas, and Roberto Diaz on improving LGBT inclusion in conferences. So that looks to be a really interesting day. So hopefully I'll see you all back here at 4 o'clock tomorrow afternoon. And until then, go and have a good day. Bye.
Thank you very much. Bye, everyone.